Hello, my name is Lindsay Clemens, and I'm from the University of Idaho, and I'm here to talk with you guys today about thalidomide, a medical mistake. So, under the brand name of Distaval, in Germany, West Germany, 1957, a new drug has been released onto the market. It's been touted as a cure for headaches, insomnia, and morning sickness. Fast forward 4 years, 1961. Around 10,000 children have been born, and half of those have died with birth defects traced back to thalidomide. Now, what happened, and how can we fix it? So, one of the main problems was that thalidomide is a chiral compound. Now, chiral compounds are pretty common, but as a brush up, chiral compounds are non-superimposable mirror images of each other, like hands. And so each different enantiomer do different things in the body. They have different bioactivity. So in this case, the R enantiomer of thalidomide was medicinal and actually did cure headaches and helped people sleep, while the S enantiomer was toxic and actually caused the birth defects. So because of this, because they didn't test for chiral compounds, and they didn't test it, especially on the pregnant women themselves, drug agencies all over the world tightened their standards on drugs. And so what they did was they made everybody that developed a chiral drug, they made sure that each enantiomer was tested for medicinal and toxic properties. Even if you were only going to use one of them in the medicine, you needed to know what both of them did, because in some drugs, such as with the case of thalidomide, even if you were to only use one enantiomer in the drug, under physiological conditions, it could change into the other one. And so you needed to make sure that both enantiomers were either harmless or had the medicinal property that you wanted. And so because of this, what a lot of medicinal chemists and chemists in general really wanted to figure out was how to separate the enantiomers. And so they ended up finding a way, and this way is the high-performance liquid chromatography. Now, high-performance liquid chromatography is pretty similar to gas chromatography, but in this case, the mobile phase is a liquid. And so in the cases of enantiomer separation, what they really wanted was normal chromatography instead of reverse chromatography. And so what this just means is that the mobile phase is nonpolar and the stationary phase is polar. And so for this particular experiment, what they used was N-hexanol in order to be an organic and nonpolar solvent. So here what they did was they used the hexanol as the solvent, and then they put the solvent into the pump. Now the pump goes through the injector into the column, and the analyte or the sample is put into the injector, and the injector also injects it into the column. And so from there, there's the stationary phase in the column. And so what that does is it slows down the different analytes until they elute at the detector. And so why this is important is you want to separate the different enantiomers so that they come out at different points. They elute at different times. And how this is accomplished is using a chiral stationary phase. And so what this does is it makes sure that the different enantiomers are attracted differently to the stationary phase. And so you get that separation of the different enantiomers. And in the case of this experiment, what they used was amylose tris 3-chlorophenylcarbamate. And so most chiral stationary phases are actually polysaccharide derivatives. So in this case, it's amylose, and then other ones also use cellulose. And this is because polysaccharides do a very good job of having lots of different chiral centers. And so you can get a lot of different attractions to different places with those. And so after it goes through the chiral stationary phase of the column, it hits the detector, and the detector, it sees how long it took for the different enantiomers to elute. And then the computer just acquires that data and shows it in a graph form, and then all of the solvent goes into the waste. Now, here are the results of the experiment that they did. The results for 3 of the different compounds. So here we have thalidomide itself. And so the little squiggle right here just shows that it's talking about both enantiomers. It's not specifying the chirality of the molecule right there. And as you can see, it has the 2 different peaks here, which means that it's separated correctly. And you can definitely see that the different enantiomers eluted at different times on this. And this is just the solvent peak. You can't see the solvent peak for these 2, but you can see where the enantiomers were separated. And so the A and RS here are just resolution and separation factor. And so you want these to be as high as possible. And you can see that the resolution and separation factor are lower for this because the peaks are closer together than these 2. And so you kind of want to maximize this. And then this one is the best one. And so what this means is that the high-performance liquid chromatography did a good job of separating the different enantiomers. And this is very important to be able to separate the different enantiomers. So we came into this because of thalidomide and the tragedy that happened with thalidomide. But because we figured out why it wasn't working, from there we were able to develop methods in order to make tests, and we were a lot more strict on our drug administration. And so we were able to make sure that the drugs we were putting out were actually good for you, and we made sure that it was as harmless as possible of a drug. And so for future work, what this paper is wanting to do is reduce the column size for the high performance liquid chromatography. And what this will do is it will allow a smaller column size, which means that we can have less mobile phase pushed through. And so why this is good is because most mobile phases are not very environmentally friendly. They're not very green. And so if we reduce the column size and we're able to maintain the same resolution and separation factor, then we will be able to have better environmentally friendly and more sustainable work using this. And so in the end, even though thalidomide was a tragedy, at least as a scientific community, we were able to rally and able to figure out why this tragedy happened and make sure that it will never happen again. Thank you. And please, if you have any questions, make sure to ask them.